So last time we talked about the Lorentzian cylinder. We talked about, of course, this product expansion and crossing equation that with an equal sign. That is the heart of this conformal bootstrap business. We talk a bit about some special cases. So for example, if you exchange identity, disconnected correlator in one channel, in the other channel, you get this generalized free field answer that is known analytically. More generally, if you put if you exchange operators of small dimension on one side, so if you imagine the kinematics where these 2 points are very close to each other, then this OPE will be dominated by the first few terms, small dimension, but on the other side, this is going to be dominated by the large order of dimension, because now you're pushing this Taylor series to its radius of convergence. So there's this nice relationship between small quantum number in one channel and large in the other channel. And for many of you, this is actually reminiscent of something else. I don't know if you've heard about the Cardy formula. So there's a trick that's very similar, which is that if you take a partition function and say the 2D CFT, that's the most famous case, and you compute it by summing over states in one channel, well, in this channel, you have a long time evolution, so it will be dominated by low temperature. And on the other side, if you compute it in the different channel, it's going to be controlled by high temperature. And using these sort of things, for example, people learn that the total density of state, total number of operator into the CFT up to delta prime goes like e to the square root of some number times c times delta prime. On the other hand, what we saw last time, in contrast, in some sense, it's a very similar game. You get small quantum number in one channel and large in the other channel. So that's the Cardy formula into the CFTs. And what is a bit here, what we got instead from playing this game using the 4-point function in Euclidean signature, instead are sum over OP coefficient square. So in one case, you're counting up all operators, and the other case, you're counting them weighted by how much they couple to exchange states. Okay. There's a whole list of other games that people can play along these lines. So for example, famous game is the light cone bootstrap, where this is the Z-plane. If you put operators in the configuration that look like this, you approach this point. This point, you see, is a little bit weird because the Lorentzian, you're approaching the light cone. This point here is approaching the light cone from 0. So the distance to 0 is small, but its distance to 1 is also small. So it's in some sense close to both, but it's not close because you have to sum a lot of terms in the OPE to get there. So what this limit does, actually, is that it controls large spin operator in one channel in terms of the lowest twist in the other channel. So another version of this relation. So I will not go into too much detail into this. I think maybe Jan talked a bit about large spin approximations. So yeah, one can use this sort of picture trying to solve the crossing equation in this limit to learn things about this large spin spectrum of CFT. There's a lot of variants of this. So this is one way of getting analytics, right? You try to have control over one side and see what it gives on the other side. And more abstractly, the control doesn't have to come from an OPE. You can also use things like thermal effective action. You can also have some effective theories of at large charge. So there's a whole lot of other topics where you can use some kind of effective field theory technique to compute what, say, a partition function would be, how it would behave in some limit, and use it to predict some properties of operators with large quantum number. Okay, so there's a whole multiple stories there. Another story maybe I will mention is if in the context of a DSCFT, if you take, we'll discuss this picture a little bit more today. If you take 4 operators, maybe with some angle between them, something like this, take a configuration like this. If you have if you're an ADS-CFT and you have a bulk that is filling the interior of the cylinder, you can imagine putting some little wave packet here that's going to create a particle that moving with a lot of energy in the bulk, and this creates some particle, and you have some collision in the middle of the bulk, and then you're recording the product at these points. So you can do scattering experiment inside the bulk by using this 4-point function. And because there's a large energy involved, and the center of mass energy here is the energy is essentially this quantum number delta, the energy on R across the sphere, the energy on the sphere. So that will tell you also something about operators with large delta. So to give you some like this, but this bulk point scattering or this bulk scattering, if you have a theory where there's a bulk, this bulk scattering gives you prediction for the OP coefficient square times the phase, where the phase just represents the fact that you have Lorentzian time evolution at the boundary to have. So you see that there's a lot of ways, different ways you can weight. So we have some sense of how many operators they are, how much they couple to stuff, and how much they couple weighted by this phase. So all of these things we can measure independently by different correlation functions. So what I want to discuss today is, so I think it would be very sad to do lectures on the conformal bootstrap without telling you like how the numerical bootstrap works for something like the 3D-izing model that we introduced in the first lecture. So I want to spend some time on this to give you a flavor of what people do, and then I will tell you some questions that come back more to this Lorentzian theme, and some first open questions there. So let's discuss a little bit the numerical bootstrap. So what we saw above here is somehow the generic way that you can get a lot of asymptotic formulas by truncating, finding some justification for keeping just a few terms on the OPE on one side, and then you learn about the other side. But what if you go away from this kinematics and study like cross this equation in its complete generality? What can we say? Well, so we have to solve this equation. Let me write it again. And now, okay, maybe I can write it slightly more precisely. There's an unknown coefficient, lambda square delta j, times one thing minus the other thing equals 0. So an equation like this, and the exchange thing is labeled by delta j. So that's a crossing equation. How do we study this? Well, it's a linear equation and is unknown, lambda square. So let's think about it from the linear algebra perspective. So there's infinitely many unknowns, right? So these scaling dimensions, they depend on the spectrum of the theory. We don't know what they are. These couplings, we don't know what they are. These things in the parentheses, they're known special function. So that is at least something we know. these conformal blocks. And so we have infinitely many unknown. Okay. And let's think for a second, how many equations do we have? Well, this equation is valid for any configuration of 4 points. So, well, we have an infinite number of equations. So we just subtract them, and how many solutions do we get? Yeah. So it's it looks like a hard problem. and I think it's fair to say that like this problem was articulated in the 70s, starting from work by Polyakov and others. There's been a lot of progress in 2D, especially, for example, there's rational models. There are cases where somehow this list becomes finite and you can like say things about it. But in the general case, the breakthrough, well, the first real step came in 2008. And the key observation is that this is not a linear algebra problem. And why is it not just a linear algebra problem? It's because these unknowns are positive. That is the key to making progress. Yeah. So what was realized was the following. So let's just try to evaluate concretely one of these crossing equations. And okay, well, one thing we can do, okay, let's try to go, we don't want to be closer to one channel than to the other, because then we're just replaying this analytic game. So let's go in the midpoint. Okay? So put z equal to z bar equal half. Right? Because the middle point between the two will be channels. They both converge equally well or equally bad, as you prefer. And let's put them. Well, actually, if you go right at this point, you get 0. Okay, 0 equals 0. It's true, but you didn't learn much. But remember, you have infinitely many equations because we can vary the point. So we can take this thing here. Let's call this function, this crossing, this combination. Let's call it f delta j of z bar. We can take a derivative and then set z bar equal half. We can compute f prime of half. And that is not 0. And it gives some interesting sum rule that these coefficients have to satisfy if the theory works, right? So if you take the sum over lambda square over all possible operator in your theory, that has to give 0. So that's a constraint on these lambda squares. And then you just plot this thing. Actually, the thing that they plotted is more like the third derivative. So they had to work like a little bit harder than what I'm saying here, but literally that's what they did. And you plot it. And here's what they discovered. So we plot this thing, f prime prime prime. And as a function of delta, that's going to be for j equals 0. In doing this plot, you also have to choose an external dimension. This is for example, I'm plotting it for external dimension 1.1, just some choice. And plot should start here. And you get a curve that looks like this. It has some 0 crossing. Let's say that's at 1.4, something like this, 2.9, making up some numbers that I hopefully are valid in these notes. And so what do we learn from this? So people who made this is Ratazzi, Richkoff, Tony, and Vichy in 2008, as I mentioned. So what do we learn from this? Well, the unknowns are positive. And so here we have a sum of positive number times this curve. So they're weighted by wherever the operators sit on this curve, right? So you can have an operator here, an operator here, an operator here. So you sum this coefficient of this guy plus the coefficient of this guy plus the coefficient of this guy. You get a positive sum, and that has to be equal to 0. But there's one thing you learn from arithmetic is that the sum of positive numbers cannot be equal to 0. And we know that the sum converge. We know that a priori from these theorems that I mentioned. So what that means is that, well, if this theory exists and is unitary, then it has to have an operator in this range. So that I can get at least one negative term in this sum. And then the theory makes sense. So basically, theory is inconsistent, so theory is ruled out. So that rules, maybe it's in yellow. That rules out theory. Rules out theory with no operator in the negative range. So notice the power of this type of argument, because we said, well, infinitely many equations, blah, blah, blah. But actually, we're able to reach some rigorous conclusion, definitive conclusion, using only one equation. Because the unknowns have a definite sign. Okay? So that particular conclusion is not very interesting, but once you see that it's possible to get some conclusion using one equation, then you try to improve and get better at this game, right? There's infinitely many equations to play with. Okay? So any question on this? Yeah. Yeah, so this special function is completely theory independent, is entirely determined by the conformal symmetry of this OD plus 1, comma 1. There's this special function that are only, it's a bit like Legendre polynomials, they just know about that. Yeah. Sorry? Why is what real? Sorry, I'm not sure I understand the question. Why is F real? Yes. Yeah, so the reason F, okay, that is actually a good question. So this F here, the way the OP arises in the unitary theory is that this is a bit like a Taylor expansion, sum over remember, rho to some power, rho bar to some power. The coefficients are real. These things here, we're evaluating them at a point where the function happens to be real. Yeah. Sorry? Yes. Sorry, I missed the word. Sorry, I just don't understand what you're saying. I just don't hear well. Exactly, the derivatives are real. Yes, exactly. So you have to take derivatives that are real. So if you put the angle, but actually, so one thing which is true and useful is that as long as z bar is a complex conjugate of z, this is real. In fact, more is true. As long as z and z bar are real, even independent, this is still real, because there's some kind of expansion like this. So it's actually very easy to make f that are real. On the other end, if you study the well, that's actually also true. But yeah, if you study the things that are more like the principal series representation that appear in theories that are not reflection positive, but are square positive. There instead, people talk about this principal series representation. You get an integral of a function that look like cosines and stuff. They're still real, but they don't have this nice positivity property. They're like cosines. Okay. But here, somehow this function naturally comes out to be positive almost everywhere. And the place where it's negative, you learn that there has to be some operator there. Yeah, if this function was just like, if this function just kept oscillating, you wouldn't learn anything from this kind of argument. It's very important that you only have one, it's not negative anywhere else. Then. Okay. Okay. And let me preventively lower this one. Right. Okay. So let's give an example of how this is used to actually learn something about the 3D Ising model. Okay. We're going to talk about the 3D Ising CFT, which is the thing that controls this critical point that we started the first lecture, okay, of either water or magnets. So from the viewpoint of this method, you don't really have to specify whether you're talking about the system of spins and so on, but you have to say something that's going to tell the equation that you're talking about the Ising CFT. And what you have to put in is the sort of information you have to put in is that we're going to study a theory that has two relevant scalars, because this is where the number of parameters we know that we have to tune in the phase diagram. So we can call it sigma, like the spin, and epsilon, like the energy density. And relevant means that these dimensions are less than 3D. And for example, experimentally, it's known that this exponent is close to 0.518. Remember that delta is like the coefficient in the power law correlation, the exponent in the power law correlation, and this guy is close to 1.41. We're going to put that the theory is a Z2 symmetry, under which this guy is Z2 odd. And well, that's it. Yeah. And then what we're going to do is that we're going to look for all the possible spectra that satisfy these properties. And the spectra, the only other thing that constrains the spectra is the unitary bound. So we consider anything that's allowed by unitarity. Bound. So that gives something like the delta of the scalars is greater than, in general, d minus 2 over 2. It's like the dimension of a free field. And of course, just adding two scalars less than 3 automatically answers that. But yeah, but that means, for example, in 3D, we're not going to scan for delta sigma less than 0.5. We're not going to bother with that region. And also, when you have spin, in general, you have delta greater than d plus d minus 2 plus 3. Okay, that is J1 or higher. And fermions somehow also satisfy the first type of condition, but we don't have fermions here. So that's all. And importantly, we require that all the unknown coefficients of these unknown guys are positive. And so what's the game? Yeah, I can just write it here. So the game. So the game. Yeah, just write it here. Just to keep order. The bootstrap game is that you generate a list of equations, basically just by taking derivatives of this f. okay? So you make a list of equations. So you try to combine crossing equation. For example, nth derivative and nth derivative of around half. So that's like a simple choice, turns out to be a good one for numerics. So you combine crossing equations, and your goal is, it's a bit adversarial. You have to take this adversarial spirit. Your goal is to combine the equation so that you can run into a contradiction and rule out whatever assumption you made. Okay? So you win by failing. Okay? It's a bit counterintuitive the first time you play it. Okay? So you combine this equation to write 0 is equal to a sum of positive times positive, and you use that to rule out assumptions, wrong assumptions. Right. So the assumption that there was nothing between, say, 1.4 and 3.9 of this plot is ruled out in that sense. All right. So the sort of simplest assumption you can make to begin are like, well, in order to run this code, I have to choose values for delta sigma for these two exponents because all the crossing equations depend on them. So basically, these are the two main assumptions I have to make. So I'm going to make these the axis of my plot. It's going to be delta sigma and delta epsilon. And then you assume that there's nothing else. There's no other scalar until dimension 3. And there's no vector, tensor, and so on below the unitary bound. And then you run this oracle that combines equation, and you find that actually some choices are not allowed. So you get some exclusion plot. I'm going to start it at 0.5 on the left, and at 1 on the vertical axis. So we get an exclusion plot that looks like this. And maybe it's more steep, matter so much. You get something like this. And this is allowed, and this is excluded. And then the first thing you ask yourself is, well, we're doing this to try to understand the Ising model. So let's see if we excluded it. We have a bug in our code or something. And this is about 0.518, and this is about 1.4 something. And the Ising turns out to be right here. The Ising CFT turns out to be right here, close to this corner. So let's step back a bit. So just the fact that you can exclude options is amazing, right? So somehow, because somehow someone realized, if an experimentalist realized one of the system, right, that we believe has satisfied these assumptions, just 2 parameters to tune, Z2 symmetry. If they realize the system and they measure the correlations and they find an exponent here, we can say, hey, you made an error. Your measurement cannot be right. Okay, it's a very strong result. It's not excluded with like 95%. It's done, excluded. Okay. So we can exclude stuff, and what you sort of, the way you should look at this sort of curve is that, well, if a theory actually exists with these quantum numbers, you should never be able to exclude it. And what's going on here is that actually the equations are able to exclude a neighborhood of this thing. And it just looks like a kink because it's starting to exclude around it, but still not very good at it. Okay? So when people see a kink, it's like excitement. Okay? It means that really your equations are discovering that there's a theory there. Okay? That's the first hint that your equations are discovering something. Yeah. If the theory was in the middle of the allowed region, then okay, we already know the theory exists. We don't learn anything. Okay. So once you get there, the next step is to throw more CPU hours into it. And actually the thing that actually pays off is not so much CPU hours, but a little bit of human hours. And for example, this plot is generated only by studying the simplest correlation function of 4 times the spin operator and making sure that it satisfies the crossing. But we said there's 2 relevant operators, and we're talking about the dimension of the guy, so why not study correlation functions of the other guy as well, right? So the way the thing that turns out to be fruitful is to study also mixed correlator. And then you can make still this. So what does that mean is that you also study this system for spin operators. The thing is easy to odd, so you can only have a even number of sigmas, but we can study a mixed system of these correlators. And when you do the OPE, these things talk to each other, because like a OPE of those 2 sigma here, I get the same coefficient as in the 4 sigma thing. But then I also get other coefficients. Epsilon goes to stuff. Epsilon sigma goes to stuff. So you get a few more coefficients, but these things talk to each other. They're not just independent equations. So they all talk to each other. And so you get stronger constraints, because you still have basically the same unknowns. And sorry, this was delta sigma, this is delta epsilon. And once you pass a certain threshold, it turns out actually that, well, the first thing that happens is that you start eating around this point, and then it becomes a peninsula, and then it starts to, sorry, I drew it wrongly. You get some plot that looks sort of like this, and so on. So like you're somehow eating around, and then when you pass a threshold, actually, you get an island, where like Ising is right in the middle. And then some other stuff further out that it's harder to exclude, but you get this thing here. And from the vertical side of this island and the horizontal side of this island, you get a prediction that if a theory exists in this ballpark, it has to have these quantum numbers. And so, for example, this scaling exponent turns out to be, is now known to be 0.518148881 ... So we can quantitatively compute stuff by ruling out all the other options. Yeah.
Can you get somehow more constrained if you also put the consistency between S and T channel or P or
okay, right. That's a great question. Yes. What about the other channel P, right? Because yeah, if you think about Feynman diagrams, you will write this equal whatever the other one. That's harder to draw. Right. You write that, and do you learn something more from this guy? That is a great question. It turns out that this guy is redundant because if you think about what's going on between this guy and this guy is that we swapped 2 of the legs, and this swap symmetry is actually a symmetry of this thing. So this swap symmetry here, we actually make manifest by restricting the sum to only even spins. And this swap is like a rotation by 180 degrees. So basically, we manifest the symmetry between those two diagrams. So this is enough. So basically, you're manifesting the equality that you, yeah. Once you impose that equality, you're manifesting the other one. That's a question. And notice these are not like Feynman diagrams. The last thing you want to write in here is like, this is not like this plus this plus this. Okay, this is not bootstrap. This are not Feynman diagrams. Yeah.
Well, so the right of that, I don't know, so like numerically about it.
Yeah, that's an interesting question. I wasn't quite able to get the status of this. I think it's been pushed past the 3. That's sort of magic number you want to push it past. But I think there are some people like Zexuan Zhang who is developing some analytic techniques to push it further. But I think there's still like some like, is there something living there? I think we don't know. We still don't know. Yeah. Right. And now, for example, the way that this very accurate number is obtained, in fact, is by looking not just as an operator, but by adding T minus, doing the so-called stress tensor bootstrap, and so on. So so by every time you add one more operator, these things keep shrinking. That is the observation at the moment. It's not known whether the method in principle converged to like a point, but like it's looking good so far. There's no indication that we hit the ceiling of this method. Yeah, that's part of the reason why people keep pushing it. Does it work? Yeah.
Crazy, but can we also use okay consistency with higher point functions?
Ah, it's a great question. Yeah. So this is in some sense, roughly speaking, you can think of stress tensor as like sigma squared and so on. So in some sense, these higher correlators know about higher point functions. And in terms of like the path of least resistance, this has been much more fruitful. But yeah, higher point functions is a bit. So I think the correct answer to your question should be yes. Higher point functions are amazing and they constrain things much more. But so far, nobody has really been able to use them. Yeah. 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 All right. Yeah. So of course, yeah, the 3D-izing model is a bit like a poster child. It's sort of fun to see you get these very accurate numbers. And of course, experimentalists cannot quite keep up, but like Monte Carlo gets pretty close. And there's actually people to compare with. So this is nice. And sort of more interesting thing that people are doing with this, and I really don't intend to do a review here, but you can try to apply this to other theories, or maybe gauge theories in 4-dimension, where you don't quite know what the space looks like, what the strongly coupled theory look like, and so on. So there's a lot of this method is used to a large extent to explore the space of theories. So we can try to go a little bit, but this is like the comfort zone that we understand very well. Okay? Right. Yeah. Yeah. Well, you see, the main thing is that if you relax unitarity, then what the only sort of game that you can really trust is a sort of analytic game I mentioned at the beginning. Like if you're very close to one limit, you can truncate one expansion to first term and see what gives on. Right, you can play a sort of analytic estimates if you relax unitarity, but in terms of like doing numerics like deep into the middle of the phase space, nobody can really do that. It's not clear how you would do it. Yeah. Mm-hmm. You're still in the convergence region, but the thing is you want to the thing is that these analytics I sketched at the beginning are so good that if you're closer to one channel than to the other, all you're going to learn is this asymptotics, which don't control so much the first few guys. So you really want to balance the contribution of the two channels. And actually, one of the difficulty, the other thing you want to do actually is that this 0.5 that we're evaluating this function, it is actually, the OPE still converge really fast. You still have exponential convergence of the OPE. And in fact, that's not what you want. Because when you actually look at what the numerics does, the numerics turns out to, you do a Taylor expansion to up to 100 terms, and you see the numerics is trying really hard to make functionals that don't decay exponentially, but like that behave a bit differently. And actually, the behavior look a bit more like the analytic functionals that I'm going to present next. So this works for numerics, but this convergence actually is not something great. The functionals you really want are functionals that with convergence is slower, so they can test more coefficients at the same time. That's sort of the intuition that people acquire from doing this. So yeah, fast convergence is not so great actually. So you want convergence, because if you manipulate infinity equal infinity, you're not. It doesn't work either, right? So you want convergence, but that's just barely. Okay? That's the optimal. Okay. So I want to set up two sort of general questions for the to orient the rest of this lecture. Is right? This sort of numerical bootstrap was very Euclidean, but still it's closely related to this space-like commutator vanish sort of statement that we saw last time. So and because we use really unitarity, which ensures that the theory makes sense in Lorentzian signature, really in some sense you can view the success as a success of this causality type of arguments. So maybe I'll just write it on the left. First question. So one question you can ask is like, okay, like what are all the implications of relativistic causality? Right. So there's this notion that you cannot send signals information faster than light, which somehow is really at the core of these equations when you think about it, right? Because from the viewpoint of a statistical system, this reflection positivity that we're imposing is really just weird. It's something that really makes sense in Lorentzian signature. So that's one question you can ask. And one thing we've seen so far is that just to make a comment about this question is that just a side comment to elaborate on the question is that okay, we've seen that it's related to crossing. This crossing equation is related to this array commutator equals 0 space-like. And in fact, the reason I call this this is called crossing is not really an accident. Crossing, when you learn quantum field theory in textbooks, crossing has a different meaning. Well, seemingly different meaning, which is that like you take an amplitude in take some scattering process in some channel, say a scattering amplitude, where you look at the amplitude for, say, electron, constant scattering of a photon, gamma, time. Like you look at the process like this, and you learn that if you reverse the sign of S, or more precisely, if you analytically continue in the upper half plane, you get to a different process, which is electron, positron annihilation into two photons. Right, and somehow this is what you usually call crossing in particle physics. It's a relation between two processes. Right. Right. And there's a branch cut also left. Right. And it's not a coincidence. It is the proof, actually, the axiomatic proof of crossing symmetry is exactly this argument. So they really are the same, the same statement. We're not going into too much details. I won't have time to go into details of this, but it's really the same notion of crossing. In fact, you can think of the same process from different channels. But that's one thing we know. But as Nima was stressing, okay, we understand like from causality, it gives you analyticity, it gives you crossing, it gives you all of these things, but like it's quite hard to test. One thing which makes it, well, if you have an analytic formula, we can sort of check. At 2-to-2 scattering, we understand. At higher points, it's less clear, but we understand some things. But like, in order to just text this, you need some kind of analytic formula. That's not so. If you just have like a numerical measurements, it's not that so obvious how to test. But in fact, for 2-to-2 scattering, we know something a bit more powerful, that once you have this analyticity and we can bound things at infinity, we get this sort of relation, that the dispersion relation, that an amplitude can be expressed as integral of the amplitude over things like this. Okay, so I won't go too much into this thing, but this is an intuitive way of a more direct consequence of a more directly testable consequence of causality. You get this relation between the imaginary part of amplitude and the amplitude. And the advantage of the interesting thing about these relations is that you can directly test them. It relates two things you can measure. Okay? All m on the real axis. Okay? So that's sort of the gold standard for understanding crossing. For understanding causality. And so, for example, a basic version of Q1 is, can we come up with some kind of dispersion relation in CFT? And that's what I will discuss partial answer to that shortly. And the other question that I want to discuss. So these are questions are partly answered and partly open. But I still want to state them as questions to sort of orient the goal of the discussion. So the other thing is that, okay, the OP converge in many times, but we also saw that the OP does not always converge in Lorentzian signature. And so what do we do when OP does not converge? When the OP sum does not converge? And we'll discuss a concrete situation that where this is needed. I'll explain why later. There's a concrete situation is, for example, this energy correlator that Jan talked about. Like this, you would think that you should be able to, if you're measuring energy in two angles are very close to each other, you would think that this energy times this energy should be equal to measuring something else at that. You should think that there's some kind of OP in the celestial sphere of these things. And as we discuss, to make sense of an OP like this, you really have to go outside of the standard OP convergence. And so it requires some extra thinking. So this sort of question, so maybe I should have mentioned this. So there's a lot of progress which is happening in the in improving this numerical bootstrap. And in parallel, there's been a lot of progress in understanding analytic properties of this correlation function and developing analytic techniques. And for the moment, it's still a bit awkward that this analytic understanding hasn't yet been possible to use in numerics. Like normally when you have better, like if you better understand the asymptotics of your spectrum, you put that into the numerical machine, it will improve. But the way it's done, the information we have right now from the analytics is not quite in the right form to help the numerics. And partly here what I'm doing is that making an excuse because the analytics has been developed to answer more like these questions than to improve numerics. Okay? So a lot of the analytic understanding in the past years have been developed to try to answer such general questions. So I want to say a few things about some ideas that have been used there, and one, I want to say what the main concepts are, and one is to try to the first concept is to try to make sense of this sort of dispersion relation, what it will look like in a CFT.
What is the dispersion relation? Are they distinct or are they?
I think they're both part of the same statement of analyticity. Yeah. So when you write down this crossing, this dispersion relation, for example, there's actually always two channels. There's a du prime. There's always two channels. You fix t and you get two channels. So crossing is somehow baked into the formula. You will never have that if you did not have crossing.
There are more by writing this way as opposed to different crossing.
Yeah, I think so, because this is a statement you can actually test for real energies. Whereas analyticity is something that like only a theorist can check. If you have analytic formulas and you check boundedness, but of course, if you check the input that are used to derive this, then you've checked it. But
Also, this measure the fact that like the cross section for annihilation, that function is the same in cross section for standard.
no, you cannot, because right, the way you do this in textbook is you you have an amplitude which is function of like minus some variable s and t. And then, very naively, you say, well, just evaluate this at minus s, or minus s minus t, so whatever is the crossing, right? But the point is that there's a different function. It's an analytic continuation of the same function, but like it's a different curve, right? So how do you check that? How do you check that the function which you can measure here is related to a function you can measure here by analytic continuation? It's a different function. It's a different looking plot, right? So this formula allows you to test this without having to talk about the middle. Yeah, thanks for the question. So this is going to be a little bit more qualitative, but I want to give some intuition about to what turns out to be the correct way to interpret this thing. So imaginary part of amplitude in scattering theory is it's like an absorptive part. It tells you how much particles you're producing. And so here we're going to study a CFT 4-point function that has kinematics that looks kind of like scattering. Like if time looks like this, it looks like, I'm gonna call this guy 1. It's a bit weird, I'm put 2 in the future, but you'll see why. 3, 4. And notice I would keep 1 and 2 space-like from each other. That would be technically useful. But still, this looks like scattering. Right? And so, like, if you have a CFT, there's no like particle, but still, if you shake the theory here, you can create a wave-like excitation that's going to hit something else here and scatter, and then you record the problem. So this is like a scattering experiment. The closest you can get to one in a CFT. And the question is, we're going to try to, as a question, what's the analog of the imaginary part of that amplitude? And we just we'll answer this at the level of analogy. And what we're going to use to answer this is we're going to use that now we know everything about operator ordering, and we know that we have many options to order the operators. So let's see the options that we have. So one option that we have, which is the obvious one, which is time order product. Right? So if you compute some correlator of 1, 3, then 2, 4. So well, it's going to be written 2, 4, 1, 3 because Dirac somehow read things backward. And yeah, that's a time order thing. And sorry, I erased the arrow of time. Right. So that's time order product. And that thing is the thing we would like to interpret as a scattering amplitude. But now, normally we do scattering in momentum space, and we always write the S matrix as, it's not really a matrix here, but still an amplitude, but we always write it as 1 plus I times an amplitude. And the point is that now we have to be careful with the I, because in position space, it always just contributes. So what this time order amplitude is really measuring, if we try to make an analogy to the best of our ability, is something like 1 plus the amplitude, plus I times the amplitude. Right, that's the S matrix, not just the amplitude. The disconnected part is there. Okay, so now let's do some more exotic operator ordering. Suppose I do something like 1, 2, 2, and then I do something like 3, 4. Oops, good. Let me drop the vacuum, so just to make it clear. Suppose you do this. Well, what's going on here? So this operator 1 acts on the vacuum, creates something great. We work really hard to create this thing. And then this operator 2 absorbs it. And then we have nothing left. And then we add 3, and then we remove it. So this is the most boring experiment ever. Like, you just measure nothing. Okay? So this is really like the 1 part. So if you wanted to just measure the 1 part, this is what you will measure. Particle 1 going to 2, nothing happening, then 3 going to 4, no scattering. Right. And by the same token, if I put, say, 1, 2, and 4, 3, it's going to be the same. It's boring. Okay. And we almost ran out of option. And notice that there's not that many options because really, because 1 commutes with 3 and 2. Really, the only question is whether 1 and 4 are ordered and 2 and 3 are ordered. So there's only one more option. And the other option is basically the complex conjugate of time order, which is something like 1, 3, 2, 4. Okay? And that, in our analogy, is going to be like complex conjugate, which is 1 minus IM. And now we can combine this and figure out what's the analog of the imaginary part of the amplitude. It's going to be something like S plus S dagger minus 2. So like we have to combine this M and M and sorry, this is M star. We have to combine those two things and then subtract the identity. And if you look carefully at what this does, this is like this, minus this, plus this. It's actually a commutator. You have to sit down and track it. And this is actually the expectation value of commutator of 2 with 3 and 1 with 4. So let's box this. So this is the thing. This is the correct CFT analog of the imaginary part of the amplitude. You have to somehow take a commutator between these two guys and average with the commutator of these other two guys. And remember that commutators are like discontinuities. So this thing is called the double disk or D disk. For some reason, this ugly name has stuck. Okay. So that's the correct analog. So now we see that somehow a more refined question of this thing is whether we can write a correlator G, Z bar as some integral over Z prime bar, some kernel, times a D disk. So an analog of the dispersion relation in CFT a physical analog of this dispersion relation should be something like this. And the question is, can we actually do this? And the answer is yes. So in fact, the correlator reproduce, so it's possible to reconstruct correlator from double discontinuity. So this analogy really carries through, and it's not so obvious. This kernel is a weird thing. It's dimension independent, so I'll give you a bit of intuition for why it exists, but somehow the physical analogy suggests it should exist, and if you work to find it, you actually find it. But the main message is that actually such a formula exists. And yeah. As long as we are in these kinematics, yeah. Yeah, if you go to other kinematics, there are many other commutators you can get. Yeah. 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 So that's the only thing you can really sort of do in this kinematics. Yeah. Let me make some comments on this thing. So so it actually has very nice properties. So just like the imaginary part of the amplitude in scattering theory is positive, this commutator square is positive. And actually, when you write its OPE in the 1,4 channel, you get something like this. It's proportional to sum over OPE coefficient times some sine square anomalous dimension. Delta minus j minus 2 delta external 2. So there's some kind of when you take this commutator in the OP, each term picks a phase, and then your commutator square give you phase sine square of that phase. And importantly, sine square is positive. So it's a nice object. It also appeared in there are relations. So this commutator square was studied also. It plays an important role for people who study chaos. So for example, the connection that I will not elaborate on, but the same object shows up in study of chaos, because if you take the large time behavior of that, you can extract some Lyapunov exponents of the theory. Yeah. Yeah, you can reconstruct, I believe, all of them. Yeah. Yeah. In some range, but definitely the Euclidean one you can get, and you can get some Lorentzian configurations. Yeah. So this is, so on the right-hand side, the integral run over the Lorentzian kinematics, but the left-hand side can be Euclidean. Yeah, thanks. So it's positive related to this other. Yeah, and this literature is called the out-of-time order. This commutator square appears in discussion of the out-of-time order correlator. So that's the same object. I want to say is that the other thing I want to say is that when you have a theory which is somehow weakly coupled, some kind of weak coupling, or even a large n expansion, even like an holographic theory at large n, this object kills all of the double twist. Kills all these operators, double twist we talked about last time. This is exactly the thing that gets killed in mean field theory. So in mean field theory, it just collapses to 0. The d-disk is saturated by identity and nothing else, and kills all up to genus 1 effects in the 1/n expansion. So at large n, So if you're a large N theory or weakly coupled theory of any sort, this sign square really makes a lot of things small. So that's very nice for analytic studies to make a lot of things small. Okay, so this type of formula has been mostly used in that context of trying to do perturbation theory in this orthographic theories, for example. What do I want to say? Yeah. See. Maybe one thing I want to say, yeah, maybe one thing I should say is that if you take this formula, remember that in the CFT lives at the boundary of a cylinder, but you're allowed to take this formula and evaluate it on kinematics that look like this on a boundary of a cylinder, and try to integrate it against wave packets that focus into the bulk, like I mentioned earlier. And what you get is that in orthographic theories, this formula actually reduced to the S-matrix dispersion relation of the bulk. So yes, S-matrix dispersion relation of bulk amplitude. Okay. So it's really not just an analogy, it really is a CFT version of the bulk dispersion relation. And as such, it's been used, for example, to constrain, so you can use this to do things that would be very hard to do directly using the Euclidean crossing equation. You can try to use it to constrain the dynamics of the bulk theory. And okay, I will just mention one of the results that's been obtained in this form is that, so Jan mentioned this morning, Jan mentioned this, center charge of 4D CFTs, which were bounded by Hoffmann-Malacena to be in some finite range. And the departure from this range has to do with Einstein plus corrections. There's corrections to Einstein gravity in the bulk, like a Riemann square correction to Riemann square in the bulk to Einstein gravity. And one of the results, for example, that's obtained is that the Hoffmann-Malacena bound are valid in any theory, but when you're in a theory which is orthographic, you actually get a much stronger bound, something with some number is not so important, but times the minimum, the square of the minimum operator with spin 4 or higher spin operator, which you think of as being, in string theory, you think of as being order alpha prime. So it actually has to be small in orthographic theory. So that's one of the sort of stronger constraints you get by thinking about these kinematics. So this sort of line of approach of using these techniques to bound effective theories, either from the flat space or from the CFT perspective, I think is something I'm quite excited about, and I think it's going to be. I think we're just starting to scratch the surface and answering the question of like what are the implications of relativistic causality. This is one tool you can use to do this. And since I'm kind of running out of time, maybe I just want to say a little bit about this connection here and in connection with like real operators, unless there are questions. Yeah.
Can they provide more constraints than just crossing, for example?
Well, they're a bit more quantitative than crossing in the sense that they're like this specific integral over something positive. So they're a bit more quantitative than crossing. They have the same input, but it's more usable. Yeah, it's a tool to massage the physics into a form you can use, into equations you can use. Yeah. Yeah, so there on the CFT side, you also have other operator ordering. I think there's a one-to-one correspondence between the operator orderings you can put in the CFT and the asymptotic observables you can do in a scattering amplitude language using creation and annihilation operators. I think there's a one-to-one map between those, but I'm happy to discuss offline. Ah, great question. The question for the future, because nobody has gotten a dispersion relation yet for 5 points. So I don't know. Sorry. Yeah, but you still have something that it should still exist some relation that relates to different objects in some quantitative way, and it's not been written down yet. It's a very good question. Yeah. So you see the higher point landscape is completely completely unexplored. Okay. So maybe I just want to articulate a little bit the question here, just to connect with this light ray stuff. So again, in this kinematics, okay, right, 1, 2, 3, 4. Right. So the 1, 4 OPE converge, and it converges like exponentially fast. Great, so we can just compute from the cross ratios here. It computes very well. Basically, an evolution from the left to the right. We can also look at the 1, 3 OPE. So if you look at this, say the time order amplitude from 2, 4, 1, 3. So the 1, 3 OPE converge also, but like with the thanks to the I epsilon. So it's like converges distribution, but it's great. And it has 2 because 1, 3 acts on the vacuum. So it does converge and it's great. But how about it? Maybe I can write it 4, 2 here, 4, 2, 1. How about the 1, 2 OPE? Well, does not converge. Okay? There's no way you cannot move you cannot move 1 and you cannot move 2 past 3 to have it next to the vacuum. So 2 operators when you don't have 2 operators that act on the vacuum, the OP is not justified. And you can actually look, and it doesn't converge, and it's easy to see it does not converge because in this limit, this variable rho that we talk about, we have a sum over, remember, it's like delta plus j, rho bar to delta minus j, and rho is very big, goes like exponential of a boost, and rho bar goes to e to the minus a boost. So this goes like x of a boost times j. Be over 2 here. So the sum over spin diverge. So in this channel, you cannot use the 1, 2 OP. It just the spin sum does not converge. There's no hope to use it. However, 1, 2 OP is exactly what we would like to have for some applications. So let's relate this kinematics to, now I'm going to state the boundary of this cylinder. So remember that the Poincaré patch looks like this. Right. And suppose I put this O3 here. Right. In order to draw a picture like Jan was drawing, suppose I want to compute energy correlator. E to the 1, E to the 2, in the state created by O. So I have a state here. It creates some bunch of stuff that are radiating to infinity. And at infinity, null infinity, you're recording the energy flow. This is an I. And And remember that Jan always had this picture with a cut. So in the future, you compute amplitude, the amplitude goes to infinity, and then you multiply by the complex conjugate, which in this picture, remember, you can draw effectively as being on the next sheet, because it's folded. So this kinematics, in this kinematics, you see that if you want to take an OPE of this guy with this guy, what you have to do is to take an OPE of these two middle guys, which are exactly the 1 and 2 in this picture. So the OPE between like real operators is exactly, this is needed for OPE of in observable. Like this inclusive energy flux in some direction. You need an OPE in that channel. Just the one that doesn't converge. Okay? So I will, since I'm out of time, I will really not, I'm happy to discuss this offline, but basically I want to just mention that there's been some progress in understanding how to do this, and actually for the EE two-point function, we sort of have a good, well-developed theory, is that the way around goes under the name of conformal rigid theory. And the idea there is that instead of doing this sum over spins, we have this exponential of boost times a spin, which does not converge, you rewrite the sum over spin as an integral over spin, where the integral runs over something like, as an harmonic analysis, something like a principal series. 0 minus I infinity, 0 plus I infinity. And now this looks more like a Fourier transform. It's like the exponent now is oscillatory. This looks more like a Fourier transform with respect to boost. And now this makes sense. And the coefficient Cj, there's lambda squared j, sorry. Lambda squared j are now evaluated at imaginary complex spin. So somehow complex spin controls this limit. And this is complex spin, and this notion that you can take the spectrum and the OP data of a theory and make sense of it in the complex plane is the heart of this thing. But it's the main way it's used is that thinking that allows you to you take discrete operators, they have to combine into rigid trajectories. And I think Jan sketched some of the things we know about the rigid trajectories in some theories, like gauge theories, and it's very much an open topic of understanding what exactly are the spectrum of these operators. But they are the things that control, for example, the angular dependence of correlations on the circular sphere and all sorts of observables of this type. But I'm very happy to discuss this more offline, but I think, I mean, I could keep going, but I think I'm I don't want to extend my welcome. So yeah, maybe just as concluding words. So I discussed some ideas which I think have been some of the ideas which really I hope will be a fertile ground in the future to understand not just conformal field theories, but like what is quantum field theory? I think yeah, so this is the, I hope this will be a fertile ground for this in the future. So thank you.